All right, welcome. Have you ever stopped to think about what really makes your phone, your laptop, or even the screen in your car actually work? I mean, deep down, it all boils down to this hidden blueprint, this one core design choice that controls everything. And today, we're going to take a tour of those exact blueprints. We're diving into operating system architectures. So what is this invisible foundation we're talking about? Well, it's the OS architecture. And believe me, the choices designers make here have huge consequences for all of us. So let's pull back the curtain and see how it's all put together. So here's the plan. We're going to start with what an OS blueprint even is. Then, we'll journey from the very first kind of messy all-in-one designs to more organized approaches like layers and modules. We'll get into the middle of the great kernel debate, check out some really wild virtual and minimalist designs, and then wrap it all up with the single most important lesson from all of this. Okay, first things first. Let's make sure we're all on the same page. What are we actually talking about when we say OS blueprint? You know, at its core, an OS structure is really just the rule book for how all its different parts are laid out and how they talk to each other. But don't let that simple definition fool you. This isn't just some boring diagram. It's the master plan that determines everything: how fast your device is, how often it crashes, and how easy it is to update later on. If you mess up the blueprint, everything you build on top of it is going to have problems. So where did this all start? Well, with the simplest idea you could possibly imagine. Let's just throw everything into one big box. Take a look at this early design. This is what systems like MS-DOS used. You can see the application right up top has a straight shot to the hardware drivers. Sometimes it wouldn't even bother going through the OS. Now, this made things incredibly fast, but it was also like the Wild West of computing. There were no rules and absolutely no protection. Yeah, and that direct access, it came with a massive risk. I mean, with basically zero walls between anything, a single buggy app could just wander into places it had no business being. This visual here really says it all. One bad program could literally trigger a domino effect and bring the entire system crashing down. Not exactly what you'd call reliable, right? This all-in-one idea eventually grew into what we call a monolithic structure. Picture the whole operating system, every single service, every driver, all compiled into one giant program called the kernel. It's all interconnected, which makes it super efficient. But just like with MS-DOS, one tiny flaw in one little piece can threaten the stability of the whole thing. So clearly, that all-in-one approach had some serious problems. To fix the chaos and instability, designers started looking for ways to bring a little bit of order to the blueprint. And that led to a new focus on layers, modules, and just a clearer sense of organization. And this search for order led to two main philosophies. Over on the left, you've got this really rigid top-down approach called the layered structure. And on the right, a much more flexible, almost plug-and-play style, which we call the modular structure. Let's dig into these. Okay, so let's break this down. The layered structure, like they used in early Unix, is kind of like a stack of pancakes. Seriously, each layer can only talk to the one right below it. This is great for debugging, right? Because if something's wrong on layer 3, well, the problem is probably on layer 3. The big downside, though, is that it can be pretty rigid and slow. Now contrast that with the modular structure seen in systems like Solaris. This is way more like a box of Legos. You've got your main core, and then you just snap in different modules whenever you need them. It's so much more flexible because all the different pieces can talk to each other to get the job done. You know, this whole search for the perfect balance between order and flexibility sparked one of the biggest debates in OS design. It's a philosophical battle that really boils down to one thing: security versus pure raw performance. So on one side of the debate, you have the microkernel philosophy. The whole idea is just beautifully simple. Strip the kernel down to the absolute bare minimum. Everything else, I'm talking drivers, file systems, network stuff, it all gets kicked out and has to run as its own separate program. And the huge win here? Well, if a driver crashes now, it's just one program that dies. It doesn't drag the entire operating system down with it. It's a design built for rock-solid reliability. So which one do you pick? The insane speed of a monolithic kernel or the fortress-like security of a microkernel? For a long time, that was the big question. But modern systems came up with a really smart answer. Hey, why not have both? And that led to the hybrid kernel. It keeps the super important performance-critical stuff inside the kernel for speed, but moves the less critical services outside for stability. It's that practical, best-of-both-worlds compromise that powers most of the devices we use every day, like anything running macOS or Windows. But wait, the story doesn't stop there. Some designers took things even further, creating blueprints that just completely threw out the old rules and rethought what an operating system even is. And this brings us to virtual machines. Let's just walk through this diagram starting from the bottom. You've got your actual hardware, your physical computer. On top of that, you have a normal host OS. But then you have this magic layer called the hypervisor. This special piece of software basically slices up the physical hardware and creates multiple, totally separate virtual computers. Each one of them can then run its own guest OS and its own apps. The power you get from this is just incredible. Because each virtual machine is completely walled off from the others, you can run Windows, Linux, and Mac OS all at the same time on the exact same physical machine. Tools like VirtualBox make this surprisingly easy to do. The hypervisor is constantly juggling CPU time and memory, tricking each OS into thinking it has the whole machine to itself. The main challenge really comes down to managing the traffic jam when they all try to use a single physical resource, like the hard drive, at the exact same time. And for our final stop, let's look at something truly radical, the exokernel. See, most operating systems try to hide the hardware from you behind all these layers of abstraction to make things simpler. The exokernel does the complete opposite. It rips those layers away and gives applications almost direct, unfiltered access to the raw hardware. Now, this is a high-risk, high-reward kind of deal. It's definitely not for your everyday laptop, but for a specialist developer trying to squeeze every last ounce of performance out of a machine, it gives them the ultimate control. So after this whole tour through decades of different designs, what's the big lesson here? What's the main takeaway? It really all comes down to this. There is no single best blueprint. There just isn't. It's all a series of trade-offs. This table right here is basically your cheat sheet for understanding those choices. Do you need absolute, no-compromise speed? A monolithic design is probably your best bet. Is stability the most important thing in the world? Then you're going to look towards a microkernel. Need a nice balance for a device you're selling to millions of people? The hybrid approach is your go-to. Every single architecture is just an answer to a different set of priorities. And that just leaves us with one final thought to chew on. We've gone from these simple, all-in-one designs to incredibly complex hybrids and virtual worlds. But, technology never, ever stands still. As our world keeps filling up with smart devices, IoT gadgets, and computers more powerful than we can imagine, the real question is, what's the next fundamental blueprint going to be built on? What will the next great OS architecture actually look like?